Hello, today we'll be looking at the urea kinetic modeling. The goal for today is to be able to use the information from the study and show the urea distribution volume over time in a two-compartment model using MATLAB. In order to determine the urea distribution volume, we will be using the urea kinetic model and the direct dialysis quantification method. From this study, we were given the following equations and conditions. From this, we made the following assumptions. We assumed that alpha, or the transcompartmental urea mass transfer coefficient, was equal to 4, that K, the clearance rate, was equal to 199 milliliters per minute. We assumed that the volume of the first compartment was 30 liters and that the volume of the second compartment was 10 liters. Our model is based upon the equilibrated end dialysis urea concentration. Going to the MATLAB program, I can open the M file that stores the code that has the given equations and assumptions stored. As you can see at the top, we have our time scale, which is from 1 to 50 minutes, and our assumed constants. We also have the given equations from the study. The last part of the code allows us to plot the urea distribution volume over time from both the urea kinetic model and direct dialysis quantification model onto the same graph. The legend helps distinguish the two curves and labels them. After running the code, we end up with this figure. However, we will get back to that later. Going back to the main MATLAB window, we see that there is now a table of values in the workspace window. According to the study, lambda 1 and lambda 2 should be less than 0, and lambda 1 should be less than lambda 2. Looking at the workspace, we can see that the values for both lambdas are less than 0. However, lambda 1 is actually greater than lambda 2. We think that this discrepancy has to do with the given equations. As you can see here, lambda 1 and lambda 2 are almost identical, but while the square rooted term is added in lambda 1, it is actually subtracted in lambda 2. Because of this, it would seem as though there is no way for lambda 2 to be greater than lambda 1, even if you were to manipulate the variables. The other condition was that A1 and A2 are supposed to be greater than 0. In the workspace window, we can see that the calculated values for A1 and A2 are both greater than 0 and satisfy this condition. The urea distribution volume at time t is supposed to be equal to negative K over lambda 2 for the urea kinetic model. Double-clicking the vector corresponding to the urea kinetic model, we can see that the value at time t is equal to 9.8. Using the command window, we can also see what our calculated value is for negative K over lambda 2, which is also 9.8. So we satisfy that condition. The urea distribution volume at time t is supposed to be equal to the total volume of both compartments for the direct dialysis quantification method. The total volume of both compartments was set to 40 liters. Opening the vector from the workspace, corresponding to the direct dialysis quantification method, we can see that at time t, the value is 39.957, which is very close to what the condition states. Despite having these conditions met, there is a major flaw in that according to the paper, the values given from the urea kinetic model should be greater than those from the direct dialysis quantification model, as can be seen in this graph from the study. Contrasting with our own results, while the two appear similar, the two curves are actually switched. Aside from the fact that we did not use the same exact values as those who conducted the study, we are not sure as to why there is this discrepancy. Despite this shortcoming, we hope that you found this video helpful, and thank you for your time.